Good morning, kids. Today's class we are going to discuss about the thermal expansion of the liquids. We'll discuss about the thermal expansion of the liquids here. We'll discuss about the thermal expansion of the liquids. So now, what is the expansion like? So when we supply heat to a body, so then the body is going to thermally expand all that what we have discussed in the solids here. Now, here I'll fill up a water. There's everything is a water. I'll fill up in a glass vessel. Okay, there's a glass vessel. Let the initial temperature of the water be 70 degrees Celsius. That's what I indicated. Then I'll supply heat. So how to heat that one? I'll keep this on the LPG flame. This particular glass vessel, I'll keep this on LPG flame. So the LPG flame starts supplying heat. Okay, fine. So then the water will start absorbing it as like a liquid, or it can be any instead of water, we can go for a liquid. Some liquid will take it. So the liquid starts heating up. So this particular LPG flames, when you supply it, the temperature of the liquid will increase. Both this glass, as well as the liquid will be expanded. Then further, as I further supply the heat, as I increase the heat, as we supply the continuously heat, the temperature of the liquid now, how much it will become? It will be 180 degrees Celsius. Then you can see that some liquid starts overflowing. So earlier, what was the level? The level of liquid was it was the volume of liquid. No? The liquid was only till here. Now look at this one. Now this is the volume of liquid. It has expanded, no? It has expanded. So if you see the earlier at 70 degrees Celsius, this was the volume of liquid. Now at 180 degrees Celsius, at 140 degrees Celsius, it has expanded. This much. So the volume of the liquid got increased. Then at 180 degrees Celsius, the volume of liquid is this much. So this shows that as when you supply heat to a liquid, when you heat a liquid, the liquid is going to expand it. The liquid is going to expand. Then, so how we define the real expansion of the liquid? The real expansion of quotient of real expansion of liquid equal to this gamma R, will say that one. This should be like change in volume of liquid by initial volume into rise in temperature. So gamma R equal to delta V by V naught into delta T. Like this, the quotient of real expansion of the liquid we can define. Change in volume, the initial volume V1, final volume V2. So this we can write it as V2 minus V1 by V1 into delta T. And we can measure the gamma. What is the difficulty we face here? We cannot heat only the liquid. Definitely we need a vessel because I have to fill up a liquid in a vessel. When we supply heat, actually, the vessel also will expand. Then the liquid starts expanding. Means I can never directly heat up a liquid. I should fill up the liquid in a vessel. I should fill up a liquid in this vessel. I'll supply heat. First, this vessel will absorb heat. Then the vessel will expand. Okay, fine. Then afterwards, the liquid will expand. Then the liquid will overflow or the liquid will expand here. This is what happens here. So these are the basic ideas. Means like solids, even the liquid also will expand. Please do like the, please subscribe, like and comment our channel, because our channel has to grow. Without your support, it's not possible. Okay, we'll take the next condition. Now, LPG flame, there's a LPG flame. Here it is there. I'll take the steel vessel. Okay, fine. There's a steel vessel. In that, water is filled up. This everything is water. Huh? This everything is water. Okay, fine. This everything is water. I'll supply heat. I'll switch on this LPG flame. So this LPG flame starts supplying heat. Then the first this steel vessel will expand. Okay, I get this. Then the heat will be transferred from the steel vessel to the water. Now the water also starts expanding. It will start absorbing heat. Then some water what happen will start overflowing here. There's a basic idea of the expansion of liquids is what we should analyze. Huh? Okay, I agree this. There's a basic idea of the expansion of the liquids. The same thing like how you define the gamma R. So gamma R equal to change in volume by initial volume into delta T. This will be a little bit difficult quantity to measure because both the solid as well as liquid is going to expand here. This was the basic scenario here. It happens. We'll take the next condition. Now, I'll fill up water in it. We'll take example of water. This is some glass vessel, glass or let it be steel vessel. Here I'll supply the heat. Initially this is I'll start eating the. So we are supplying this using an LPG flame, or you can keep this in Bunsen burner. Here, let gamma of the liquid be gamma L. Alpha of the liquid, alpha of the solid, let it be alpha S. So what is gamma L? Coefficient of volume expansion of liquid. What is alpha S? Coefficient of thermal expansion of solid. Like this, we are defining it. Solid or the steel vessel. Your liquid means here water. Now I'll supply heat. Okay, this LPG flame will supply heat. First, what happened? The solid will expand. You can see this was the initial volume of solid. Now look at this. It has become like this here. So solid will expand. Then the heat what happened will from solid will be given to the water. The steel open vessel will transfer the heat to the water in all directions. It will transfer it. Then the water also starts expanding. You can see earlier the volume of water was this much. Now the volume of water is equal to this much. Then you can see that there is no overflow. Absolutely, there is no overflow in this particular case. And initially fully filled up. 'This will write it here. it is fully filled up. So what was the initial volume of the vessel? That was the initial volume of the water. Then finally also, as I rise the temperature, there's no, so like a overflow. So this was earlier T1 degree Celsius, now T2 degree Celsius, where T2 greater than T1. Then there's no overflow. What does it mean? How much the steel vessel expanded, that much what will happen? The water will, that much the water will expand. So for this, so definitely what we can say is, what is the condition? Gamma of the liquid equal to 3 times of solid. When do this will happen? When initially, when the liquid fully fills up the solid, on rising the temperature, on rising the temperature, if there is no overflow, and again, if the liquid fully fills up the solid, then definitely you can say that how much the solid expanded, that much what when the liquid will expand. Then definitely what when the volume expansion of the liquid should be equal to volume expansion of solid. There's a one possibility. Next, other possibility. Again the LPG flames. Now, will so this I'll switch on the LPG or Bunsen burner. So many sources are there. We can take help of that. I'll switch on the again next type of liquid. So some liquid may not be water. Some other liquid. Let this be a steel vessel. Then I'll rise the temperature. So earlier, what was the temperature? Here, now the temperature is again some other liquid, need not be water. It is, let's assume that it's fully filled up. Now I'll rise the temperature. I will rise the temperature. Then the solid, the steel will expand. The steel will expand. If the liquid level in the vessel decreases at higher temperature, what does it mean? Then the solid expanded more than that of this liquid. No? Then what is the condition will arise? Gamma L less than 3 alpha S. There's a possibility. Huh? Some liquid. Here, if the liquid expands less compared to the solid, then the level of liquid, final level of liquid will be less than to the level of the solid. Means here, it will not reach to the brim of the vessel. It will be somewhere this level only it will reach here. When do this will happen? When the liquid expands less than solid. Next, I have another situation. Another liquid I'll fill up. So initially we'll assume that instead of water, we'll assume that it is some liquid fully filled up. I'll rise the temperature. So again, how to rise the temperature? The LPG flame will supply the heat, or the Bunsen burner will supply it. Then first the steel vessel will absorb it. Earlier this was the volume of the vessel. Now this will be the volume of the steel vessel. Now the liquid what happened will overflow. The liquid will overflow. Then what does it mean? The liquid expanded more than that of the solid. So here gamma L greater than 3 alpha. Here liquid expands less than the solid. Here liquid overflows, or both liquid as well as solid here will expand equally. Here solid expands more than the liquid. Here, liquid expands more than solid. So if initially if a liquid is fully filled up in a solid, if you rise the temperature, again, if the liquid fully fills up the solid at higher temperature means gamma L equal to 3 alpha. Initially, liquid is fully filled up. Liquid is fully filled up in a solid. Will rise the temperature. If the liquid doesn't reaches to the brim, we'll call this a brim or the edge of the solid. Definitely what will happen? The solid expands more than or liquid expands less than the solid. So initially we'll fill up some liquid in a vessel, will rise the temperature, will increase the temperature, will increase the temperature. Here, if some liquid overflows, then definitely what you can say the liquid expands more than this solid. Then what is the condition? Gamma L equal to 3 alpha. Like this, the ideas is what we can put here. Here we'll write it. Liquid and solid expands equally. This is one basic idea of the thermal expansion of the liquid. Now we'll take the what do you mean by apparent and real expansion of the liquid. So here liquid is filled up. This is in a vessel. So initially the level of liquid is at A. We'll do this marking. This is at A. Then as I start supplying the heat, what we are supplying the LPG flame, Bunsen burner flame, any of the available things. So I'll supply the heat. So first, actually, oil expand means the vessel will expand. First, as this supplies heat, first the vessel will expand. This vessel will expand because this vessel is a solid. Then afterwards, it will transfer the heat to the liquid. So because of that, the level of liquid inside the vessel will slightly decrease, will fall off. So it will be come to the B. Liquid has not yet expanded. Now here what we can say is solid expanded or initially vessel expanded means due to rise in temperature. So due to rise in temperature, here the level of liquid at the vessel expands. As the vessel expands, the level of liquid what will fall off. The level of liquid will fall off. The reason for that, definitely as the vessel expands, the volume of the vessel will increase. The volume of vessel will increase. Then the level of liquid will fall off. So it will come like this. Now continuously this LPG flame will be supplying the heat. And as it starts supplying heat, now this vessel will start transferring heat to the liquid. It will start transferring heat to the liquid. Agree this. Now what will happen is the liquid starts expanding. Now the liquid starts expanding. So here what we can write here, the liquid will expand and the level what we can show it something like this. Let me draw it properly. So the level of the liquid has come till here. This is the temperature, you say T1 degree Celsius. There's a final temperature T2 degree Celsius. Now liquid expands. So this, I'll do marking. This is A, this is B. This BC will be the real expansion. And what we see the AC is apparent expansion. The AC will become the apparent expansion of the liquid. This AC apparent expansion. The real expansion will be from B to C. Okay, so this is not visible. This second diagram will not be visible. Cannot be. And this we are able to. This is visible. And this is visible. It's most of the situations practically when you switch on this LPG flame, as it starts supplying the heat, as it starts supplying it, the vessel will expand. The fall of liquid in the vessel, this we don't notice. Sir. What we notice is this one, the level of liquid is at A. And finally, at temperature T2 degrees Celsius, the level of liquid is at C. So this AC, what we are able to measure is apparent expansion. Real expansion is not measurable. Only has to be calculated. So what is noticeable means only apparent expansion of liquid is noticed or can be tabulated. We can calculate. Actually, this real expansion means actually the liquid will expand from B to C. This is not visible. Initial level of liquid in the vessel is at A. Okay, after rising temperature, it has become to T2. Only this much is what we have here. So how to measure the real expansion of liquid? Therefore, the formula is what we are going to derive it. So initially, let the volume of liquid be V naught. Volume of vessel also, let it be V naught. So then volume of liquid, let it be VL. Volume of solid, let it be Vs. Then by the definition, final volume of liquid equal to initial volume of liquid 1 plus gamma L delta T. Final volume of solid equal to initial volume of vessel gamma S delta T. Then the change in volume delta V equal to VL minus Vs, which is equal to delta L is equal to, we'll define this as V naught 1 plus gamma L delta T. V naught gamma S delta T. Delta V is equal to V naught delta T. Then what is this particular thing? Gamma L minus gamma S means expansion of liquid with respect to solid. Gamma apparent will write it into delta T. So what is the gamma apparent? Gamma apparent, gamma L minus gamma S, or in short, gamma A equal to gamma L minus. We can also write this as gamma A. So apparent expansion of liquid equal to real expansion of liquid minus real expansion of solid. Or we can also write it as apparent expansion equal to real expansion minus 3 times of real expansion of solid. The same thing. This thing is, so what is measurable here? The apparent expansion is measurable. So this only that the apparent, instead of gamma apparent, we are writing symbol gamma A. Apparent expansion means expansion of liquid with respect to solid equal to expansion of liquid minus expansion of solid. Expansion of liquid is what? Real expansion. Expansion of solid is real expansion of solid. This is the expansion of liquid with respect to solid. So how we define these terms, we'll write it here. So all those things will indicate them. So what is the gamma L real expansion of liquid? Next, gamma apparent expansion of liquid. Next, we are having the gamma R real expansion of solid. What do you mean by apparent expansion? What is the meaning of this? Apparent expansion means expansion of liquid with respect to solid. Expansion of liquid with respect to solid. So this particular thing is called as the apparent expansion. And what is measurable? Measurable not measurable. So therefore, from experiments, I know real expansion of solid. I know most of the vessels, I know their alpha value, glass, steel, anything, or solid, any of the solid. I'll measure apparent expansion of the liquid. Then I can use this formula. I'll find out the real expansion of liquid. So therefore, the formula now will become gamma R equal to gamma A 3 alpha S. In most of the cases, the solid will be chosen as a glass. So the real expansion of the liquid is equal to expansion of liquid with respect to solid plus 3 times of expansion of solid, 3 times of linear expansion of solid. So further this particular gamma R, so we will write it as 3 alpha G. Means expansion of real expansion of liquid is equal to apparent expansion of liquid with respect to solid, or expansion of liquid with respect to solid plus 3 times of linear expansion of solid. Like this, we have defined the basic formula. So this what we'll be using in the all our problem solving. Okay, students will discuss with this particular problem based on the thermal expansion of liquids. The quotient of apparent expansion of liquid in gold vessel is G, and when heated in a silver vessel is S. The quotient of linear expansion of gold is A. Find the quotient of linear expansion of silver. So what is the basic formula? The quotient of apparent expansion of liquid in gold vessel is G. So expansion of liquid with respect to gold equal to expansion of liquid minus expansion of gold. What was the given? The coefficient of apparent expansion of liquid in gold vessel is G. So therefore here gamma Lg, I should write it as G. And find the, and is telling coefficient of linear expansion of gold is A. So therefore what shall we write here? This should be equal to 3A. Then apparent expansion of liquid with respect to silver equal to real expansion of liquid minus real expansion of silver. What is the apparent expansion of liquid with respect to silver is S. Then gamma L 3 alpha S. So we'll replace gamma L here. Gamma L will be G plus 3A minus 3 alpha S. So alpha S equal to linear expansion of silver needed. Equal to G minus S plus 3A by 3. So what is actually happening? There is a gold vessel inside. Okay, there's a gold vessel. I'll fill up a liquid. Then this will have the A expansion of the gold is, let it be 3A, or will be A will be linear expansion. That of the liquid is gamma L. Next, I'll take silver vessel. And again, I'll fill up a liquid in it. Fine. So this is the silver vessel. Silver vessel. And here, this we have to find out alpha S. I'll measure them. I'll say G, then expansion of liquid with respect to gold, let it be G. Expansion of liquid with respect to silver, let it be S. From the data, I can measure. So if I can measure G, S, and I know A, I can bring the real expansion of the silver or expansion of the silver. A simple idea-based problem. Okay, fine. I'll take the next problem. Please do subscribe and like and comment so that our channel will grow and will survive. I will take the next problem. Next, a liquid occupies half of a vessel at a particular temperature. Then the volume of the unoccupied part remains constant at all temperatures. If alpha and gamma the quotient of linear and real expansion of vessel, then. So of all very important is this particular thing, unoccupied part. The volume of unoccupied part remains constant at all temperatures. So based on this data, we should find out the required relation between gamma by alpha has to be found out. Half of a vessel occupies half of a vessel. So how do the basically suppose this is the half of is occupied. We can assume this liquid will fill up half of the vessel. Exactly, you can see it. Half of it is present. So here the initial volume of liquid, let it be VL. Volume of solid, let it be VS. This is a vessel. Then I'll rise the temperature. I'll rise the temperature, both liquid as well as solid. Both will expand. the unoccupied volume remains constant. So now where I have to show the liquid? Liquid I have to show it somewhere here. This will be the liquid. So we expanded, liquid expanded, solid, both liquid as well as vessel, both expanded here. This is at T2 degrees Celsius. We are going to supply heat. Then because of heat supplied, first the solid will expand, then liquid will expand, and finally this is the unoccupied part is telling. So this is the unoccupied part. And this part should remain same. This volume should be equal to this volume. I think it can happen. I'll write this unoccupied part, let it be delta V. So now the new volume of the liquid is how much? VL dash. New volume of solid is VS dash. This unoccupied part remains as it is, will not change. Delta V naught, all delta V naught. About unless this we have rise in temperature. T2 degrees Celsius greater than T1 degrees Celsius. So what is actually this? This is the unoccupied part, and how much it is? Half it is. So what is the initial volume of the liquid will be equal to half of the volume. When I supply heat, liquid and solid vessel as well as liquid both will expand. Then what was this volume? It has to remain same. It's not telling half, not like that. This unoccupied part should be as it is here. Okay, no? This is so now what we do is like we will write the equation. So initially, what is the volume of the what was the initial volume of the solid? Vs minus Vl should be equal to Vs by 2, which is equal to delta V naught. Then finally, Vs dash minus Vl dash should also be equal to delta V naught, which is equal to Vs by 2. What is Vs dash? We'll expand it. That should be equal to Vs 1 plus gamma delta T, and VL will be VL dash will be 1 plus, I'll write next term here, 1 plus gamma L delta T. This should be equal to Vs by 2. So why delta V naught? Why you are writing delta V naught equal to Vs by 2? Because what was the initial unoccupied part will be half of the volume. Now also it has to remain same. So this should be equal to Vs. What was the initial volume of the liquid will be Vs by 2. So from here, initial volume of the liquid, if you solve it, it will be like this. So what is the initial volume of the liquid? That should be equal to how much? Should be equal to Vs by 2. 1 plus gamma L delta T Vs by 2. So Vs I think will finally what we get here, gamma S equal to gamma L by 2. So now what is so we want the quotient of linear. So gamma S will become 3 alpha S. So alpha S equal to gamma L by 6. So he's asking the ratio gamma L by alpha S should be equal to 6. This should be our answer. He's asking to get the ratio. Requesting all students to please subscribe, like, and comment on our channel so that we can survive. Okay. Okay, this is our answer. So for my channel to grow and survival, definitely it all depends upon your support. Without your support, I'm not in this position. So all watching this video, please do subscribe, like, comment, share to your friends. Let it get everyone benefited with this, the free knowledge available. Okay, fine. So these are the some simple diagram based question. So, sir, how to draw the diagram? Diagram is what you should able to imagine a vessel half filled, unoccupied. When you supply heat like this, the vessel will expand. Even the liquid will also expand, but unoccupied remains same. Rough diagrams you draw a little bit easy for you. Look, we'll discuss one more problem on the thermal expansion of the solids. A vessel is half filled with a liquid at 0 degrees Celsius. And this is 0 degrees Celsius. A vessel is half filled with a liquid at 0 degrees Celsius. When the vessel is heated to 100 degrees Celsius, when vessel is heated to 100 degrees Celsius, the liquid occupies 3/4 volume of the vessel. Find the coefficient of apparent expansion of the liquid. One more small idea-based problem. Is asking to calculate the apparent expansion. If vessel is half filled, we'll assume the diagram. We'll bring a small diagram. Okay, this is a vessel. It is half filled. This is at 0 degrees Celsius. Okay, fine. Now I'll heat up this vessel. When you supply heat to this, it will expand. Both the vessel as well as liquid will expand. It occupies 3/4 of the volume. 3/4 of the volume of the vessel. New volume or the initial volume? I think I'll show next a bit. It's telling 3/4 of the volume of vessel means it should be initial volume. Now the liquid will occupy the 3/4 of the volume of the vessel. So earlier, what was the volume of filled? This is at 100 degrees Celsius. Now, what was the initial volume of the liquid with respect to vessel? Initial volume of liquid with respect to vessel is V/2. What was the final volume of liquid? Will be 3/4. So we know final volume, initial volume, change in temperature. We can calculate the apparent expansion. So you define the apparent 3V/4 is equal to V/2. Final volume of the liquid equal to initial volume 1 plus gamma A into change in temperature 100. So this will become 3/2 equal to 1 plus 100 gamma A. 3/2 minus 1 equal to 100 gamma A. So this will become 5 into 10 to the power of minus 3 per degree Celsius. This will be the apparent expansion of the liquid. Okay, there's a one basic method what we can apply here. Just based on the data, 3/4 of volume of the vessel. Okay, fine, kids. No? Thank you, all of you. So we'll take the next problem. Now let me read the question. The figure shows a glass tube. I think there's a glass tube. Linear quotient of this would be alpha, completely filled with a liquid. Okay, this yellow color is something all, everything is a liquid. This is a vessel, glass tube. Okay, this everything is a liquid. Volume expansion coefficient. On heating, the length of the liquid column does not change, find gamma. This is gamma. On heating, the length of liquid column does not change. So what is our entire question? The figure shows a glass tube. Linear coefficient of this is alpha of the glass tube. It is filled with a liquid whose gamma of the liquid is quotient of volume expansion of the liquid is gamma. On heating, the length of liquid column does not change. Means this length. So when we heat it up, I think this particular glass tube will expand. The glass tube will expand. Then proportionally, what should happen to the length will not change. I think some rough diagram is what I'm bringing up. So what is happening is that the liquid is also expanding, but this length will not change. Now the new area, let it be. Now the temperature earlier, T1 degree Celsius. Now how much temperature it will be? T2 degree Celsius. So this particular length will not change its filling. So how to calculate the find gamma? We have to calculate gamma in terms of alpha. There's a condition. So who will expand here as the solid will expand? Now area of cross section, we'll try to write A in terms of A naught, area of cross section of vessel in terms of A naught, where A equal to A naught 1 plus 2 alpha into delta. I'll multiply L naught on both sides. So what was the A L naught will be the final volume of the liquid, initial volume of the liquid. Look at this one. So what is the final volume of liquid is V. Initial volume of liquid is V naught. Initial volume of liquid is equal to initial volume of solid. Final volume of liquid is less than that of the solid. Vs dash you that. Hope you are able to understand. Now, this final, the liquid is expanded. V naught 1 plus gamma L delta T. So therefore, this gamma L V naught get cancelled. So 1 plus gamma L delta T equal to 1 plus. So what is the basic mechanism here is earlier the liquid is fully filled up in this vessel. Okay. I'll rise the temperature. T2 now how much? T2 greater than T1. Because of this vessel will expand up. So it has become this much. The liquid also will expand. Earlier, what was the volume of liquid? Volume of liquid is only this much, no? V naught, no? It is equal to volume of the solid only. Now, this is the new volume of liquid. Liquid got expanded, you can see. Level didn't change. The level didn't change. But you look at the area of cross section has increased, so the liquid has expanded. Solid also expanded. You can see that this was earlier volume of solid, now this is the volume of solid. Okay, Vs dash. I'm just considering the area expansion of the solid equal to A naught 1 plus 2 alpha delta T. I'll adjust L naught on both sides. Now this V is the volume of liquid, which is equal to initial V naught into 1 plus gamma L delta T. Solving will get it here. Okay, fine. This will be your answer. I'll take the next problem. A cylindrical tube of length 100 centimeter contains some mercury inside. If the length of the remaining liquid air column remains constant at all temperature, find the height of mercury. Neglect the expansion of cross section of the vessel. And he has given gamma of mercury and gamma of the tube. How to manage this? I think some diagram. If you draw the diagram, things will be easier for you. Area of cross section, the vessel will be same. So we'll start like this. This is the so this is the initial level. So we'll write length of the tube H1, length of the liquid column BH1. Mercury, mercury only. And this is glass. Temperature is raised. Both glass as well as mercury will expand. So what the condition is put is like, if the length of remaining liquid air column remains constant. So this is A, no? This length will remain same. No? No, this as expanded. I will write H2, glass expanded. Similarly, the mercury also expanded, right? H2. Hope you see. So like if you draw the diagram, little bit easy for you. The analysis will be easier. So first we will expand, the glass will expand. So this this is a glass. What was the initial length of the glass at initial temperature? H1. When you rise the temperature, yes, the glass will expand. Now it will become, you can see directly see this, the length of glass increase. Now this was the length of the mercury column. Length of mercury column is this much. Length of mercury column is this much. Then after rising the temperature, now this will be the length of the mercury column. You can see there's an increase. So new H2, earlier H1. Height of the glass tube is H1. When you rise the temperature, it become H2. So we'll write the equation. So this you can write it as T1 degree Celsius, T2 degree Celsius, and we have increased the temperature. We'll write directly the equation. H2 is equal to H1 1 plus gamma S delta T. Similarly, for the liquid column, H2 mercury column equal to H1 1 plus gamma L delta T. And what is the condition given? H2 minus H2 is equal to H1 minus H1. And this everything is equal to X. You can see from here. This length will remain same. This length will remain same. Length unoccupied or the length of air column will remain same. So therefore, we are able to write this one. I'll substitute the value. H2 will be H1 1 plus gamma S delta T. No, the height of the mercury column, the initial height of the mercury column is being asked. I think that can be easily tabulated now. H1 gamma S equal to minus of, okay, what is H1? H1 given 100. So therefore, H1 is equal to substituting all the values, we'll get the required answer. This will be 100 centimeter or 1 meter. Gamma S or gamma 2, both are same here. This will be 2.7 into 10 to the power of minus 5. Minus 6. 2.7 into 10 to the power of minus 6 by gamma L will be 18 into 10 to the power of minus 6. Solving this, we'll get the, this will be 9 by 6, 3 by 2, 1.5. 15 centimeter or 0.15 meter. Both are same. Huh? Okay, what is the condition? I think this last condition is very important. Neglect expansion of cross section. The area of cross section, what is there, will remain same. Huh? This condition given. So therefore, we are assuming it. Practically, even the area of cross section will change, but the condition given, it's not expand. Maybe the glass is designed in such a way, the vessel. Okay, kids, we'll take the next problem. It's now we'll discuss the problems based on the thermal expansion of the liquids. So here, when a specific gravity bottle filled with mercury at 0 degrees Celsius is heated to 100, 5.190 gram of mercury overflows and 300 gram remains. So what is the specific gravity? So it's like a something bottle like this. So initially it contains some liquid. Okay, fine. Then when I expand it, so when I rise the temperature, the bottle will expand. And the liquid will also will expand. This is some just rough diagram, and some overflow will be there. So what amount of earlier liquid we don't know. 5.190 gram overflow, and the remaining how much will be 300 gram. Specific gravity bottle. Usually this is made up of glass. So both will expand. Earlier theta 1 degree Celsius. This will be theta 2. So with the help of this, what we can find out is apparent expansion. We can. So this is the expelled liquid. Expelled mercury. This is the remaining mercury. So we'll write it here. Expansion, apparent expansion. Expansion of mercury with respect to specific gravity bottle is equal to this apparent expansion. What is the formula? In general, what is the formula? Apparent expansion, coefficient of is equal to, the formula will be mass of expelled liquid by mass of remaining liquid into rising temperature. This is one generalized formula. So what is the mass? What is the mass of expelled liquid here? How much it is? 5.190 gram is expelled here, no? So we'll find out gamma of mercury with respect to specific gravity. Apparent expansion of mercury with respect to specific gravity bottle, that should be equal to how much he has given. Mass of expelled liquid 5.190 gram is expelled. We'll directly write the value 190 by mass of remaining liquid and 300 gram remains in the specific gravity bottle. Some delta T, 100 degrees Celsius. I think solving this will get the gamma. Similarly, again, what is being done? Glycerin is used. Next condition. Next, what I do is like I'll take the glycerin, means in the same specific gravity bottle. I'll fill up glycerin. Okay, fine. So this will be glycerin. Initial temperature 0 degrees Celsius. Directly the data given 0 and this is 100. Thermal expansion occurs. And 27.33 gram of glycerin will remain as it is inside it. And some will overflow. Expelled glycerin. So how much will be expelled? 1.439 gram, and this is 100 degrees Celsius. So this is a specific gravity bottle. Instead of glass, better write water. Usually they are made up of glass. This similarly, again using same formula, apparent expansion of glycerin with respect to specific gravity bottle equal to mass of expelled liquid. This is expelled liquid. Expelled glycerin, how much it is equal to? 1.439 by 27.33 grams is what remaining. Okay, solving and what is, okay, solving this will get some value. Gamma ms equal to gamma of mercury minus gamma of specific gravity of bottle. Similarly, gamma of glycerin with respect to specific gravity bottle equal to gamma of glycerin minus gamma of specific gravity bottle. It's asking now real expansion of the glycerin. I think substituting this here, gamma S will be equal to gamma M minus gamma MS. Quotient of real expansion of mercury given value. We know this value. We have calculated this apparent expansion of mercury with respect to specific gravity bottle, apparent expansion of glycerin with respect to specific bottle, and real expansion of the glycerin is what needed. That can be tabulated. So this we have to substitute all values. So just can you work out? I don't have something calculations to be done. Okay, let me calculate. This 5.190 by 300 solving, we are getting this much. Similarly, 1.439. Now 5.190 by 300 into 100. So we'll get this much. Apparent expansion of glycerin with respect to specific gravity bottle solving, we are ending up this much here. 1.439 by 27.33 into 100 will end up this. So these values will substitute here. Let me solve further. Gamma GS will be 5.26 into 10 to the power of minus 4. Minus real expansion of the mercury, 1.8 into 10 to the power of minus 4. We'll subtract all 5.2 minus 1.73 minus 1.8 will be 1.67. This is of the glycerin. Okay, there's a one formula which you have to remember. This is very, very important. Okay, all of you. So we got this answer. This is our answer. In exam, you should be very fast in calculations, no other way. So please try to remember this formula is very important for us. Quotient of apparent expansion. This is one experiment here. It's not it's like experiment. Quotient of apparent expansion of a liquid. Quotient of apparent expansion of liquid is equal to mass of expelled liquid by mass of remaining liquid into rise in temperature. And there's one important formula where we can calculate the apparent expansion of liquid. Once you know apparent expansion, we can calculate the real expansion. Okay, kids, so these are some problems which I'm discussed about related to the thermal expansion of liquids here. Coming class, we'll discuss few more some better problems where some good application oriented things are available. So please do revise. There's a best thing is what happened. You have to revise, rethink. Then only you'll get a clarity. So please do subscribe, comment, like, share this channel to all your friends, relatives who are all there. Thank you for great support. So we'll meet next week. Again, the same extension of expansion of liquids. Again, on Wednesday, I'll upload the video so where you can explore the still more best problems. Okay, thank you all of you.